Hello students, today we'll be starting one of the largest chapters of class 10, which is the chapter known as triangles. Now, until last year, you studied triangles from the perspective of, obviously in younger grades we studied basic properties of triangles, things like angle sum property, the side length properties. Then we discussed different types of triangles, scalene, isosceles, equilateral, right angle. And then last year in class 9, we studied congruency, where how we can figure out if two triangles are congruent, meaning they are exactly the same. So this year, we will be doing a similar concept, except instead of doing congruency, we will do something known as similarity. Now, before we get into similarity of triangles, let's quickly understand what it means for two figures to be similar. So when we say something is similar, obviously in English terms, similar means things that look like each other, that they can be related. But similar does not mean same, because then I would just use the word same instead of the word similar. So the good way to remember it is that same is congruency, which we did last year. Similar or similarity, as we will study it, is when two figures look alike but are not exactly the same. And specifically, similar figures are those which have exactly the same shape but are of different sizes. What that means is two squares are similar. So let's say one square is this big and another square is also there, but the other square is this big. Now we say that these figures are similar because they have the same shape, but they are not congruent because they are of different sizes. Similarly, all circles are also similar. We know that if I look at two circles, any two circles, obviously I have one circle like this and I'll have another circle maybe that's slightly bigger, but they're still circles and so they still look similar. And so we will be discussing similarity of triangles. And just like in congruency, we had things like SSS, SAS, etc., etc. In similarity, we also have certain conditions and we will look at them and solve it. So just before we start with similarity, we're going to learn a couple of theorems that will make understanding similarity a lot easier. And these theorems are the basic proportionality theorem and of course its converse. So let's look at those two. So we will first look at the basic proportionality theorem, or for short form, the Bpd theorem. Now the Bpd theorem states that if I have a point on a side of a triangle and I draw a line parallel to the second side of the triangle intersecting the third side, then the parallel line will divide both the sides of the triangle it intersects in the same ratio. So this is known as the Bpd theorem. Now we are going to prove the Bpd theorem because this year you can be asked to prove theorems in the exam, and it is in fact very common and it comes as 3 markers or 4 markers. So it's very important to be comfortable with the proofs. And so let's start with proving the Bpd theorem. Now, so first, as we do with all proofs, we will draw our figure. And so we have our triangle over here and we'll draw our parallel line through it over here. Now, let's name our triangle. So let it be triangle A, B, C. Let this be a parallel line DE. And this is our triangle, and it is given that DE is parallel to BC. Now, the way we're going to prove it is, obviously first we have to write to prove, and all we need to prove is that the ratio AD upon DB is equal to the ratio AE upon EC. Because obviously this is what it means for the parallel line to be dividing the two sides in equal ratios. These are the ratios. So to prove this, we are going to do a couple of constructions, which are, first we will join DC and BE. So join DC and BE, and we will draw DF perpendicular to AC such that F is on side AC, and EG perpendicular to AB. In other words, what I am doing is I am joining BC, joining DC, drawing a perpendicular from D to A, and drawing a perpendicular from E to AB and from D to AC. And of course, like I said, these points are nothing but, let this be point DF and let this be point EG. And so, given that this is perpendicular. Now, we know that the way we're going to deal with this is we will be using some properties from last year and just some basic logic. Now, it is given to us that the line DE is parallel to BC. That means that the area of triangle DEC, which we'll just look at the figure, will be equal to the area of triangle DEB. That is, area of triangle DEB is equal to area of triangle DEC, because they are triangles between two parallel lines, and we know from last year that means that their area is equal. Similarly, obviously we know that area of triangle ADE is equal to area of triangle ADE, just because it is the same triangle. Right? This is because of triangles between parallel lines, and this is because of, it's obviously the same triangle. Now the reason we're doing this will become clear to you. I'm going to write that we are going to add these two equations. So adding the above two equations. That means area of triangle DEC plus area of triangle ADE is equal to area of triangle DEB plus area of triangle ADE. Now you might be thinking, why are we doing this? What is the purpose of doing something like this? That will become clear when we write out the areas of these triangles using half base into height. Let's look at it very quickly. If I look at triangle DEB, the area of triangle DEB is equal to the area of triangle DEC, which we got earlier. Also, triangle DEB plus triangle ADE is nothing but triangle AEB. Similarly, area of triangle EDC plus area of triangle ADE is nothing but area of triangle ADC, which means that when I do this, this implies that the area of triangle AEB is equal to the area of triangle ADC. And now the area of triangle AEB, this triangle, is nothing but half base into height, where I will take the base as AB and I will take the height as EG. And so this is equal to half, this means half times AB into EG is equal to, similarly for triangle ADC, it will be half times AC into DF. Now, obviously half and half will get cancelled and we'll be left with, this implies that AB into EG is equal to AC into DF. Now, so the reason that we have done this is that we will now basically shift certain things around, simplify it, and then from there get our answer. So now that we have written these two things, that area of triangle DEC is equal to area of triangle DEB, and obviously area of triangle ADE is equal to area of triangle ADE, what we're going to do is we are going to divide these two equations. So if I say that let this be 1 and let this be 2, we're going to do 1 divided by 2. Now that means what I'm saying is that obviously this is equal and this is equal. It means that the area of triangle DEC divided by the area of triangle ADE is equal to the area of triangle DEB divided by the area of triangle ADE. Why are we doing this? Because it will become clear when we actually write out using half base into height the areas of these four triangles. Now area of triangle DEC, which we see is over here, area of triangle DEC, if I take EC as the base, the altitude will be DF. So that means area of triangle DEC is half into EC into DF. Similarly, area of triangle DEB, by taking DB as the base, will be half into DB into EG. So let's write these two first. So area of triangle DEC, as we've established, is equal to half into EC into EG, and area of triangle DEB is equal to half into DB into DF. Half EC into DF and half DB into EG. So I need the figure in these questions.
Again problem?
No, because I need to see the figure now to know what sides I've used. So not a major problem, we'll start from here. It's just going back and forth is a little difficult. I'll look at
You
it
can put that in it's not on the...
No, I made my own figure, na?
Okay.
So it's different. That's okay. I mean, now I know what to take, so it's not a huge
Let's do it
problem.
then.
Yeah,
Okay.
no problem.
Good. 3, 2, 1, go.
So the area of triangle DEC, as we've just seen, will be equal to half into the side DC, or the side EC actually, half into EC into DF. The area of triangle DEB will be half into DB into the side E, as we saw there, EG. Now this will be divided by, obviously, on both sides. That's why I put one line, although technically we should take two different lines for it. So it will be equal to half. So for area of triangle ADE, now when I'm taking it with DEB, I'm going to use the same height as DEB. So I'm going to take it in the first case as half AD into EG, and for the second case I'm going to take it as half AE into DF, right? Which will just be determined by which side I want. So since over here I have EC, I'm going to take it as half into DF, or obviously DF would be the height that we want, and so it will be half AE into DF, and here it would be half, since it's DB, so AD into EG. And so what you can see is that half and half will get cancelled, DF and DF will get cancelled, half and half got cancelled, EG and EG got cancelled. We are left with, this means EC upon AE is equal to DB upon AD, which if I just write it as a reciprocal, it means AE upon EC is equal to AD upon DB, which was what we wanted to prove, that this upon this is equal to this upon this. And so this basic proportionality theorem will be used to use similarity in the future. So let's first solve a few questions based on basic proportionality and then move on to actual similarity of triangles. So looking at a couple of very quick applications of the basic proportionality theorem, I'm just going to make a couple of sample triangles, and we're just going to solve some small numericals. These can usually come for 1 mark in the exam. So let's say that we are given that there's a triangle ABC, and then of course DE is parallel to BC, and you're given that AD is 1.5, DB is equal to 3, of course centimeters, so 1.5 centimeters and 3 centimeters, AE is equal to 2 centimeters, and you're asked to find the length EC. So of course we will simply say that since DE is parallel to BC, this means by the basic proportionality theorem, AD upon DB is equal to AE upon EC, which implies 1.5 upon 3 is equal to 2 upon x, which if we see, that means x is equal to 4. And so like this, we will basically determine questions. A slightly more advanced version of this question could be something like this, where I have a triangle given to me and I might have more than one variable in terms of what I'm looking at. So perhaps you can have a situation where we're given that, once again DE is parallel to BC, and let's say in this situation they give us that AD is 1 centimeter, BD is 3 centimeters, and that the entire entire length AC is equal to 8 centimeters. And we have to find AE and EC. Now to do that, obviously if I know that AC is 8 centimeters, that means I can take AE. If AE is X, that means EC would be equal to 8 minus X, because obviously AE plus EC is equal to 8. And so from there, we'll get that again by BPT. We know that AD upon DB is equal to AE upon EC, which implies that we have the case of 1 by 3 is equal to X upon 8 minus X, which clearly means 8 minus X is equal to 3X, which means that X is equal to 2. 8 is equal to 4X, X is equal to 2. And so that means that over here AE is obviously equal to 2 centimeters and EC is equal to 8 minus 2, 6 centimeters. And this is the way that BPT is used to solve basic simple questions revolving around basic proportionality. So now that we understand BPT, let's move on to the main part of the chapter, which is similarity of triangles. So let's look at a couple of more proof-based questions on BPT. So we're given a figure in which we have triangle like this, and we are given that is a shape like this inside it, like this. Now I'm going to name this triangle, let it be triangle ABC, and let this be EFG over here. We have to prove that AE upon EG is equal to AG upon GB. And it's also given that, of course, these extra lines that I drew, it is given that FE is parallel to CG and FG is parallel to CB. So while this question might look complicated on the face of it, it's actually a very straightforward question. When we look at the sides that they've asked us, we have AE and EG and we have AG and GB. What this means is, since they're consecutive sides joined by, an intersecting point, it probably means that we have to use BPT in some way, shape or form. Also, we have parallel lines, and so all we need to do is identify the appropriate triangles and go from there. So, for the proof, let's start out by using FE parallel to CG. Now, if FE is parallel to CG, that means in triangle ACG, since FE is parallel to CG, this means by BPT, we will have AF upon FC is equal to AE upon EG, which is the first of the two sides that I wanted. Let this be 1. Now, similarly, if I look at FG parallel to CB, I'll take triangle ACB. So in triangle ACB, as we have over there, in triangle ACB, over there we had, so AF upon FC will be equal to AG upon GB. So again, since FG is parallel to CB, then by Bpd, AF upon FC will be equal to AG upon GB. Let this be 2. And so we clearly see that I had AF upon FC here, I have AF upon FC here, which means 1 is equal to 2, and therefore it means that AE upon EG is equal to AG upon GB, which is what we were asked to prove. So when you get questions like this in Bpd, the main goal of the question is very straightforward. It's simply that we need to prove certain things. What are the triangles? What are the parallel sides in the triangles? And from there, get our answer. Let's look at one more, a reasonably challenging type question, and then move on to similarity. In this question, we have been told that we have a trapezium ABCD such that AB is parallel to CD. So AB is parallel to CD and it is a trapezium, right? As we can see here. We have been asked to prove that AO upon OB is equal to CO upon DO, right? So even this OB, BO doesn't really matter. Where obviously AC and BD are the diagonals and O is the point of intersection of the diagonals. So whenever we have parallel lines and we have ratios given, it's another hint that it's a Bpd question. And what we're going to do is, we're going to do a construction, very simple construction, where we're going to say, draw some other point, EO parallel to DC, where E is from the side of AD. And the reason for this will become very clear. Now, because I have taken EO parallel to DC, that means in triangle ADC, since EO is parallel to DC, this means by Bpd, once again, we have AE upon ED is equal to AO upon OC. And what we see is I have some form of my O's with AO and OC here. And so let this be equation 1. Now, since we drew AO parallel to DC, it means EO will also be parallel to AB. Lines parallel to the same line are parallel to each other. So we'll just write that out. Since EO is parallel to DC and AB is parallel to DC, this means that EO is parallel to AB. We will use this in triangle ABD. So in triangle ABD, or I am actually going to write it as in triangle DAB, since EO is parallel to AB, it means that DE upon EA is equal to DO upon OB, which we can see over here, that DE upon EA will be equal to DO upon OB. If I take the reciprocal of this, this means that AE upon ED, I took reciprocal and just rearranged the sides, is equal to OB upon DO, which is now equation 2. And it is clear that equation 1, AE upon ED, is equal to equation 2, AE upon ED. And so, since 1 is equal to 2, this means that from the first one, where we had AO upon OC, is equal to, from the second one, OB upon DO. And so, by cross multiplying, this means AO upon BO is equal to CO upon DO, which is what we had to prove. And so this is the primary thing that you will be focusing on in BPT questions. You find the appropriate triangles, get the ratios and equate them. So now let's move on to actual similarity of triangles.